on one binary out of the box. And you really are dealing with a set of binaries that are dynamically linked together. And so if you go from a call from the application into a system library into NTDLL that leads to a system call, you have to count up, you're going to need to know the entire usage of the stack for that to determine if it precludes exploitation of a stack overflow in an exception-protected block later. And that kind of stuff is not dealt with well within current disassembly tools. There could be some modifications, you could retrofit that functionality. Hopefully we'll see it in the future. We have more work to do on it, but we believe there will be a lot of success in automatically finding good cases that maybe require you to examine application-specific behavior here.
Okay, so we're going to cover one last thing, which is pretty quick and straightforward. So we'll talk about exception handling in G++ and Unix. It's a considerably different design from Windows in two ways. First, there's really no underlying SEH mechanism provided by the system. So system-level faults aren't really mapped into the G++ runtime exception handling. I mean, it's possible you could try to throw an exception within a signal handler, but basically how you're going to get notification of system-level faults is through hard signals. The other major way that G++ exception handling differs from Windows is that all the information is actually kept out of band, sorry. So there's no exception records on the stack. It's all kept in a database in 3 separate L sections. And basically there's 2 databases. One that tells you for any given function that you're in, it tells you how to unwind the stack, restore the machine state, and get to the calling function. And then there's a separate database that tells you how to match thrown exceptions to handlers, and also it tells you how to deallocate automatic variables. So what's interesting is this is implemented. Now there's a legacy implementation using set jump, long jump, but the mainstream case is implemented using dwarf style encoding information. So it's basically like an ELF debugging subsystem that's used in runtime to handle exceptions. It's kind of crazy. And the dwarf style encoding is very much a pain to decode because it's a variable length encoding. Anyway, so there's 3 ELF sections, EH frame, and this effectively has an entry for each function, and it tells you if you're in that function how you can unwind the stack frame. And it also has 4 references to the other database. The EH frame header is basically an index in EH frame. And the GCC accept table tells you how to match exceptions to catch blocks and how to destroy automatic objects. So basically, how this works is pretty crazy. For any valid EIP in the program, it has a database that tells you if you're at that EIP, how to restore the machine state and get to the calling frame. So this database is actually compressed programmatically. So there's little programs in these ELF sections that are run through like a little VM. So there's a little opcode language to actually generate the information necessary to be able to unwind stack frames. So the other this will come into play in a second. But the other database basically marks off ranges of instructions in the program as what it's called call sites. So basically what these are is if an exception is thrown in a certain range of addresses, then the call site tells it what to do. Anyway, I think we're about out of time, so I'll just skip to the conclusion. Basically, the stack unwinding done by the G++ exception handling is done out of band of the normal stack unwinding. So normal function epilogues and prologues aren't called. So if you have a situation where you have a buffer overflow, it overwrites the cookie, and then you can cause an exception to be thrown before that function returns, the stack's going to be unwound by this separate mechanism, and it's not going to do stack cookie checking. So basically you can use that to bypass stack cookies. And the way you do it is because the database uses the saved EIP to look up how to unwind the stack for that given EIP. So basically you overwrite with a saved EIP that points at a catch block somewhere else that does something interesting, and then you actually control the save ESP from there. And obviously, having programmatic little opcode things in writable sections at relatively fixed addresses is interesting. So that's it.
Yeah.